Hi, my name is Phil Jelinek. I'm a retired auto shop teacher from Monrovia High School. I spent 26 and a half years teaching auto shop in Monrovia, California at the high school. These are some of the principles that I used that incorporate STEM principles in the classroom. And after reading the articles about STEM, these are practical applications of how to incorporate STEM principles in the classroom. So first of all, let's take a look and see what an internal combustion engine is. First of all, internal combustion engine. Internal combustion. Internal means inside. Combustion means burning. So basically, an internal combustion engine, the power is developed where the fuel is burned, versus an external combustion engine, which is basically a steam engine, where the fuel is burned separate from where the power is developed. So, an internal combustion engine, this is what we have. So we have this area where the combustion takes place is called the combustion chamber. All right, so let's take a look and see how all of these parts are interconnected. We have to get some basics down so that we get the terms correct. All right, the first term I would like to explain is top dead center. So we have a piston, we have a connecting rod, and we have a crankshaft. Picture a bicycle. When you're riding a bicycle, your legs are the power. In other words, basically the piston. The crank, your feet go on the crank, and they end up to be pushing the connecting rod. The connecting rod is the rod that connects the piston to the crankshaft. The crankshaft is that crank, and it changes the up and down motion of your legs into rotary motion. So that's what we do here. So we have piston, connecting rod, crankshaft. All right. From top dead center to bottom dead center. Now, the dead centers mean the center of the connecting rods are lined up with the cylinder. So the distance between top dead center to bottom dead center is called a stroke. The distance from bottom dead center to top dead center is also called a stroke. Now, when we start dealing with the four-stroke cycle engine, it takes 4 strokes to complete 1 cycle in the four-stroke cycle engine. So the first stroke is called the intake stroke. Now, we have valves here. They're basically openings, and they're controlled by a timing belt or timing chain, and this controls and makes sure that the valves open and close at the proper time in relation to where the piston is in the cylinder. So when the intake valve opens, now we create less than atmospheric pressure. Atmospheric pressure then flows into and pushes air and fuel into the cylinder. So we call that the intake stroke. Then we close the intake valve, and now we squeeze the mixture, and we make it into a much smaller area. Then we use our spark plug to ignite that air-fuel mixture. The result is a rapid expansion of heated air. Now, most people will call it an explosion. I just like to call it a rapid expansion because we have to be able to explain the difference when we start talking about octane ratings. When you go to the gas pump and you put in 86, 89, or 92 octane, the higher the number of octane, the slower the rate of burn. So we have to be able to explain that, and just saying an explosion doesn't cover that. All right, so we ignite the air-fuel mixture. The result is a rapid expansion of heated air. It pushes the piston down. This is where we get the power from. The other 3 strokes don't contribute anything to the running of the motor. It actually takes power away. All right, so then we open the exhaust valve, and we push the burnt gases out, and we're all ready to open the intake valve to start the next cycle. So it takes 4 strokes: intake, compression, ignition and power, and exhaust. And that completes the cycle. So we call it a 4-stroke cycle. Now, there are other engines out there called a 2-stroke. I'm not going to go into that here. So intake, compression, ignition and power, and exhaust. Top dead center to bottom dead center, and stroke. All right. How do we measure an engine? Now this is an actual engine from a cylinder from a Volkswagen engine. This engine had 1,600 cubic centimeters. Now there were 4 cylinders. So 1,600 cubic centimeters divided by 4 means each combustion chamber is 400 cubic centimeters. Now the combustion chamber is when the piston is at bottom dead center and the distance from here to the top of the cylinder head, this is called the combustion chamber. Now this is a cubic centimeter, and I like to use stuff like this to help explain and give visuals to my students as to what they are. And so I would have to be able to fill 400 of these would have to fill up the combustion chamber for this particular engine. And so you get an idea of the volume that we're talking about. The same with cubic inches. If I have a 350 cubic inch motor, there's 350 cubic inches, there's 8 cylinders. So divide 350 by 8, and you come up with about 39.4 cubic inches per cylinder. So again, this is a unit of volume. All right. The other measurement I would like to arrange or talk about is the carburetor or air intake. You know, we don't have carburetors anymore. We have fuel injection, but we do have air intakes. We have to be able to measure the amount of air. So the carburetor mixed air and fuel, and it went through what we call a venturi. Now a venturi is a closed off area. And what I have here is a removable venturi to help you understand. And basically it's just a restriction for the airflow. And when we start rating carburetors or air systems, we rate them in cubic feet per minute. This is a cubic foot. Again, I like to be able to explain to my students what a cubic foot looks like because most students don't have a clue and they have a hard time picturing this. And so I try to have a cubic foot here to help people understand. All right. So now that we know the basics of the internal combustion engine, let's do a demonstration. Now this demonstration, people don't get to see what is actually going on inside the internal combustion engine because it's all covered. Everything is covered and you never get to see it because we have burning taking place inside. I like having my students understand what's going on inside the internal combustion engine. So I saw this in a Mr. Wizard's display and I incorporated it into my classroom and became one of my students' favorite demonstrations. Now, a couple things that I can't do that is done in the internal combustion engine. I can't squeeze the mixture. So using Charles' law, where when you compress a gas, it generates heat. So I'm bringing my own heat with me because I can't actually squeeze the mixture. And then when air and fuel come in, the valves help rotate the air and fuel and help mix the gas with the fuel. I can't do that either, so I will be mixing the fuel. I also have a small hole here, and I'll use one of these barbecue igniters, and this is how I will light my internal combustion engine, and then you'll get to see internal combustion. All right, so I'm going to start off, and the fuel that I'm using, this is not gasoline. Please don't try this at home, but I will use a fuel that's rated for this kind of effect. And so this is my intake stroke. I'm going to have fuel injection here, so I'm going to inject the right amount of fuel into my combustion chamber. This is my piston. So I'm going to put this on, and of course I'm going to make sure it's down very tight. And then I have to allow the heat, to actually build up, and then I have to actually mix the air and fuel. And of course, in the internal combustion engine, this happens in microseconds. All right, and then once we get that to happen, I'm going to ignite the air-fuel mixture. Now, a couple of things you should have noticed. Once I ignited that air-fuel mixture, it rapidly expanded the air by heating it. When the pressure got so much, it pushed the piston off away, and you got to see some of the combustion come out. So combustion is a rapid burn. It's not a straight explosion. So it's just a rapid burn. So as the piston was pushed away from my internal combustion engine, you got to see it. And that was part of the exhaust. Now, this piston, we would connect to a crankshaft, and that would, again, change the up and down motion of the piston. And we would end up doing this again and again and again. And it would convert it into rotary motion, something that we can use. All right. So this is our internal combustion engine. So, you know, if we look at this, this is what's taking place. You know, my intake stroke, we open up the air and fuel mixture, we draw air and fuel in here, we squeeze the mixture, we ignite the air fuel mixture with our spark plug, and we push the piston down, and then we open up the exhaust valve and push the burnt gases out. And this all takes place very, very quickly. Well, how quickly? Well, the only way we can explain it is by using math. What is actually taking place is the piston starts at top dead center, accelerates, comes to a dead stop, changes direction, accelerates, comes to a dead stop. That's one revolution, and it takes 2 revolutions to go through the whole 4-stroke cycle, so that each of these valves are opening once for every 2 revolutions. And that's something that we need to pay attention to as we move along. Okay, this is our informational display. Most people will call it the speedometer, but it's actually your informational display. It gives you all the information that you need for the operation of the vehicle. When you turn the ignition key lock assembly on, all of these lights will come on to let you know that they're working, and in 1 second, most of them will go out. And then the rest of them go out once the engine is started and running. All right, so we have 2 major dials here. The first one is measuring the speed of the automobile. We measure that in miles per hour. The other is the speed of the engine, and we measure that in revolutions per second. So first we're going to do miles per hour. All right, so we're going to use math to help us explain. So miles per hour, so we can just write it mph, which is the way it is written on that dial. But miles per hour is actually a fraction. That's what we're actually saying, miles per hour, and it's a fraction. Now we know what hours are. Hours are broken into 60 minutes, and each minute's broken into 60 seconds. But what are the miles? Where do we get miles from in measuring an automobile moving? Well, the only thing connected to the ground are the tires. So we have to be able to measure the tires. So basically, if we take a tire, and you can do this at home, and if you just draw a line of chalk on the road and on the tire, and then roll the tire out until that line comes back, draw another line, and then measure the distance between the two, and take that distance and divide that into 5,280 feet, you'll get how many revolutions of tires goes into the 5,280 feet. Now, through gearing and other uses of math, we have a gauge here that will convert that to miles per hour. And so this is where we get miles per hour, actually measuring the circumference of the tire and how many revolutions it makes over a period of time. All right, so we had to go there first before, at least I feel we have to do that before we go to the second one, so that you understand what we're actually doing. Now the other dial is revolutions per minute. Now, what's a revolution? A revolution is the piston starting at top dead center, accelerating, coming to a dead stop, changing direction, accelerating, coming to a dead stop, and changing direction again. So that's one revolution. It's important to understand that because we need to know how fast things are going. So revolutions, RPM, is actually revolutions per minute. Okay, it's a fraction. Now, revolutions per minute. Most vehicles will operate about 750 revolutions per minute. Now, this dial here has got 1, 2, 3, 4, 5, 6, and 7, but each of those numbers is times 1,000, as it says in the lower corner here of this dial. So this is 1,000 RPM, 2,000, 3,000, 4,000 revolutions per minute. Now, most cars idle at about 750, but for our demonstration, we want to make it math simple. So the car that drove you here today, or the car that you use, idles at about 600 revolutions per minute. Now, if we tried to generate enough speed and over a period of time, and we tried to do this for a minute, it would take a long time. You know, I'd get tired doing this, you'd get bored watching it. So let's try and change revolutions per minute to a smaller amount of time so that we get a true sense of what's actually going on. So if we change minutes to seconds, now before we do anything here, you know, we're going to need to change the minutes to seconds. So we have 60 seconds per minute. Now, before we deal with the numbers, we have to make sure our terms are correct, because if our terms are not correct, then we know our numbers won't be correct. Now, we can divide terms as long as the denominators are the same. These are the same terms as any number that we have. All right? So when we have two fractions and we're dividing them, what we end up doing is we invert the denominator and then multiply. So we have revolutions per minute times minute over seconds. The minutes divide out and we're left with revolutions per second. So now we know the terms are correct. Now we know our numbers are going to be correct. So at 600 revolutions per minute divided by 60 seconds per minute, you know, the car that is your normal car that's in your driveway at idle, it's operating at 10 revolutions per second. So in the amount of time it takes me to make one revolution, 1001, the car that you own did 10 revolutions. Each valve opened up 5 times because each valve opens up every other revolution. So each valve opens up 5 times. We had 5 ignition cycles per second during that time, per cylinder. So if you have an 8-cylinder car, this is taking place on each of the cylinders. Okay, now, we have this, on this dial here, we have what we call a red line. As fast as you can go safely with that engine. So at full throttle, how fast is the engine actually going? So again, for math, most cars are about 6,000 RPM. So that's what we're going to use, okay? At 6,000 RPM, we just add another 0 here, it changes the revolutions per second to 100 revolutions. Now things are starting to get a little complicated. Not complicated, there's a lot of things going on at once. In the amount of time for the standard vehicle that you're going to be driving, in the amount of time it takes me to do one revolution, 1001, your vehicle traveled at 100 revolutions in that same amount of time. Each valve opened and closed 50 times a second. It's like, wow, 50 times a second, 1001? That's a lot. We had 50 ignition cycles per second per cylinder. A lot going on. Now, let's take a look at race cars. Now, race cars, they're actually designed to go faster. They actually redline out at 12,000 revolutions per minute. Divided by 60, how many revolutions per second is that? Well, that's 200 revolutions per second. So, what does that mean? So the amount of time it takes me to do one revolution, 1001, a race car at 12,000 RPM did 200 revolutions in the same amount of time it took me to do 1001. That means each of these valves opened 100 times per second. Now, there's no way to get that across without math. Math helps you explain what's going on. So this is why we need math. We had 100 ignition cycles per second, giving us 100 power strokes per second per cylinder. There's a lot going on, a lot moving, but we're not done. What happens to this race area we call Formula One? In Formula One racing, they are limited to 18,000 RPMs. 18,000 revolutions per minute. All right, so at 18,000 revolutions per minute, how many revolutions per second is that? It's 300 revolutions per second. So in the amount of time it takes me to do one revolution, 1001, a Formula One engine has done 300 revolutions. It's like, wow. Each valve is opened up 150 times. Why don't we just leave the valve open? Well, that's because of fluid dynamics, other laws of science. We need the pulses. So the valve has to open up 150 times per second. We had 150 ignition cycles per second, per cylinder. There's a lot going on in these motors. So, this math is used to help you understand, it's a language to help you understand what's going on, so that I'm not saying, well, in the internal combustion engine for race cars, this goes really, really fast. There's no other way to explain it except with math. Okay, let's take a look at one other aspect of, when we have a Formula One engine, now we have a lot of air being needed going through our venturi. And most carburetors, like this carburetor, is rated at 600 cubic feet of air per minute. Now, if we do the same math that we did here and change minutes to second, 600 cubic feet of air per minute is 10 cubic feet of air per second. So if we have a venturi, that means every second, 1001, 10 of these cubic feet of air has to go through per second. Then you start to realize, boy, that's a lot of air trying to go through this little opening. How do we do this? Well, the way we do this is we use the Bernoulli principle. All right, I'll get my assistant over here. And this is called the Bernoulli bag. And what this bag is going to do is help you understand the Bernoulli principle. All right, now I'm trying to fill this bag up with just the air in my lungs. All right? So if I try and fill this up, it would take me probably about 5 breaths to fill this up. But if I use the Bernoulli principle, I can fill this bag up with 1 breath. How can I do that? Well, you notice there's a difference in what I did. Instead of just using the air in my lungs and putting it up here to my mouth, I went about 6 inches away and then blew in. I created a less than atmospheric pressure here, and then atmospheric pressure pushed the air in and then filled the bag from the back up. Watch. So you see how you could see the air go in, and then all of a sudden it filled the bag up and completely filled it up. This shows you, by using the laws of science, we can get massive amounts of air through a small opening like this by just restricting the airflow in that short little area. Thank you. All right, let's take a look at cooling systems. Most cooling systems in books, they only mention 2 cooling systems. Cooling system by liquid, in other words, liquid surrounds the combustion chamber, and convection, in other words, air coming, air cooling or air coming off of the cylinders. There's actually 4 cooling systems once you apply the rules of science. The first cooling system, now we have 2,500 degrees, upwards of 150 times per second here going out the exhaust. So guess what? Our #1 cooling system in the internal combustion engine is the exhaust system. So that's our #1 cooling system. Over half of the heat of the motor goes out the exhaust. Our second cooling system is the liquid cooling system, and that surrounds the combustion chamber and helps keep the metal and draws the heat of combustion away. Our third cooling system is the lubrication system. That actually cools the bottom parts of the engine and the valves, the top part of the engine. And then normal convection, and this is an air-cooled motor. See, the one cooling system we can do without is the liquid cooling system. We've proved it with the Volkswagen